Hey guys, um, back with another LeetCode Path to Pro video. Today, it is Saturday, May 6th. Taking a few days off, a little lazy. I think I've been doing LeetCode problems though. Maybe not. Did I do them? I think I did a couple yesterday. Yeah. Nothing yet today though. Um, but yeah, today, and if you'll notice, I'm in a different spot. Yeah, traveling, whatever. Uh, I'm just duck sitting. Um, so yeah, today I'm going to solve 112 path sum. So this problem is another binary tree problem, and it's another. This one's a little more interesting than a few of the previous binary tree problems where it's just asking for depth and stuff like that. This one I think is a little more interesting. So we're given the root of a binary tree and an integer target sum. Return true if the tree has a root to leaf path such that adding up all the values along the path equals target sum. A leaf is a node with no children. Alright, so this first example, if we look at it, and this is our root node, and this is the leaves they were talking about. I think these are just called branches. But basically, in this example, we're given a target sum of 22. So if we go look, we start here, that's 5. At our root node, that value, like the root.val. Then plus 4 is 9, plus 11 is 20, plus 2 is 22. Okay, cool. And then here, we are given target sum 5. And there's no way to add up to 5 going from root to leaf. Because we go to 1 to 3, it's 4. 1 to 2, that's 3. So, yep. And I think this is another DFS problem, right? And I'm going to do it recursively because it's just a lot less code. So if not root, we're going to return false. That's just that third example. This is an edge case, right? If the root they give us is empty, it's false. There's nothing, no matter what the target sum is, because it's going to be an integer. Yeah, integer. You have to have an integer, but so if the root's empty, we have to return false. Yep. And then we're going to have another, so we're going to look to see what's another edge case. Another edge case is if they give us just the root and the root. So like let's say in this case target sum is 0, and in this root node it was 0. So like if root.val equals target sum and not, this is how you do the correct, not root dot right, dot left, we are going to return true. So I think that's the correct syntax where we're saying not. Instead of I was trying to do like equals false and all this stuff, I think it's just not root dot left saying it's null. So in this case, right, we're saying, okay, there's a root and it's 1, and our target sum is also, lucky enough, happens to be 1. If these equal, we're just going to return 2. And now we want to get to the meat. How could we do this? So what we could do we could do it like, we could just basically subtract as we go down through the tree. So we have our target sum, and we go down minus node.val. Is it node.val or root.val? no. Yeah, probably node. Right, so this is just gonna, and then we have to recursively call this as past something. So we can do return. We'll say if how do we recursively call it? Is it return? Oh, return false. Return self dot as path sum, and we want root dot right. Some, excuse me, and then why didn't that copy? I don't think this is quite correct, but this is probably pretty close. Node. Got a couple corrects. It's interesting. Okay. So it works for this one. What's it not working for? Expected false. We're returning true for this one. So right, because what we're doing with this return is we're saying, okay, run this again, return the result of looking down the right path, and I think returning 0 is true, false. Yeah. So 0 is true. So, right, and our target sum should be 0 if there's a path down the right or the left side. Right? Why? Why would it be returning true for that? Because it should be returning false. Let's just see. I'm curious. Is this going to stop us at? Can we look at the test case? Oh, jeez. Huh. Let me see. This might help. It's my the dog snoring. I know, I'm so confused what's going on with this guy. The fuck? Oh, man. Because, right, well, we can try. Not a bad idea. So what's it? 2 on the left. back. Left. And if it's a balanced binary tree, wait, balanced binary search tree, I think is the correct term, then it would be 2 up here, 1 on the left, 3 on the right. But anyways, I think that's right. So how is this returning true? I'm curious. I want to see if it will return false. Let's just take this out and see if it will return false for that third disk. Okay, well, you need that. So something's up. Because I'm looking on the right side both times. Obviously. Gosh. No? Okay. I thought that would fix it. Oh. God, excuse me. Sorry, bro. So. Oh, jeez. Root that right. Why? Like, how is one of those returning true? I don't know, I kind of want to look at solutions and see where. We look at left first. I wonder if order matters. Probably not, but just make totally certain. Alright, yeah. Let's see. A solution. Swing waiting. Zone waiting. Say or. We need an or statement. Is that why? We don't want both these. We just want to say or. Well, I thought that's what I was doing. Was I doing like a return both? Interesting. Because maybe it was like, okay, it was calling it when we had both, and it was saying 2 plus 3 equals 5 somehow. Okay, but yeah, that works. So you got to put the or. And the time complexity, memory complexity is, however many calls this is going to make to the stack. And the time should just be O of n, because we're going to look through. What would it be more? Because you might look through more, like, let's look at a really big example. Oops. I'm going to do that. Or, I think that's the word. Got it. Got it, man. Got it. It's not working. So we got a dot here. Just draw a big tree. Ooh, this is ugly. It's binary tree, so right. I'm just gonna check to see, are we ever gonna go? Well, yeah, you are gonna go through the same node, right? Because you can go through this node. We're gonna go through this node a ton of times. This node. So I wonder if it's O of n log n. Or some other time complexity, right? Because log n, where you're basically going through, you're like cutting your sample size n in half each time. I don't know. Ooh. Right, because like if I can go through, okay, this is our first run through, and then now we're going through those two again. A second, so you see we're going through 1, 2, 3. These three are all repeated that we're gonna check. So yeah, I wonder if it is O of n log n time. But yeah, thanks for watching, guys. See ya.